Hey everyone, welcome back. So today we have with us Andreas Krivas. Andreas is addicted to solving complex problems and dedicated to helping the world gain confidence in today's rapidly shifting technological landscape. So after trying electrical engineering, mechanical and software engineering, he started as a cloud native engineer and now from the position of engineering manager at Container Solutions, Andreas helps clients improve their business by creating tailor-made solutions that enable them to leverage the cloud. Please welcome Andreas.
Hey everybody, very excited to be here, sharing with all of you what I've learned over the last few months. Starting sharing my screen. Hope you can already start seeing that. Right, I hope that everybody's having a great time so far with the keynote and the opening of Chaos Carnival. Today and in this talk, I'm gonna take you through in the rabbit hole that's called network chaos. It's gonna be quite challenging, so I hope that you have your coffee and you're ready to dive in with me. Um, a few words about me. Very few words. Don't want to bore you with myself, but I'm managing manager at Container Solutions, also senior software engineer there, and I live in the Netherlands. And over the last year, I've been a consultant for many years now, but over the last year, I had the privilege to work in a very interesting project, which is basically today you're going to see the results, or at least some interesting solutions that we came up with during our time in that project. And hopefully the problems that we faced are going to resonate with you as well. Um, Feel free to ask any questions. We're going to take a few questions just before the demo because we're going to also break some things together today. And at the end of the sessions, we're going to take as many questions as possible, but feel free to reach out also later if you want to have more information about what we're going to discuss about today. So, very simple, brief agenda. We have a problem. Hopefully this problem will be something that you will also recognize. We're going to discuss about a solution. There are more solutions out there, of course, but I'm going to guide you through a solution that worked very well for us, and I think it's going to be a very useful solution for many of you out there. Like promised, we have a demo, and then some final takeaways and conclusions at the end of the session. So let's start with the problem, right? Now, microservices, right? I guess many of you have already heard the word microservices or microservices architecture, or hopefully you're already working with this kind of architecture principles. But it's basically something that we see a lot nowadays, right? Companies or systems that are built in microservice architecture in mind. And if you're really curious about microservices and you really like working that way, you probably have stumbled upon Sam Newman, a very prominent speaker and author in the community around microservices. And I'm not going to go in depth about what Sam Newman says about microservices, but I think these 7 principles that you see now in the slide are very key, right? And it relates directly to what happens when we have a lot of microservices eventually. Things like high observability, right? Being able to see what's happening in your system, isolating the failure. When something fails, not more things fail. This is the goal. Decoupling of things, that's one of the core things in microservices, and so on, right? This is, I hope, something that you've seen so far. The question is, what happens when you start from a small system and you start to migrate or develop more applications or microservices, and you suddenly end up with this. This is a dependency graph of a few thousand probably microservices. It actually has a name in the slang that we have in Cloud Native, and it's called a ball of mud because it actually looks like one, right? And you can imagine that this becomes a very difficult thing to manage and operate confidently, right? And that in a way that you know that it's resilient enough. And especially the more it grows, the bigger the problem, right? one application fails, then things start to fall apart. And this is where things become difficult, right? When you hear words like, well, I don't know why this failed, right? Or an application fails and suddenly a seemingly unconnected or completely irrelevant application breaks somewhere else in the environment. Or that we can't deploy in a dedicated way. We can deploy one application because it will break other applications. Things like that, right? And one of my favorites is that things fail and then takes weeks even to figure out what's the root cause. Right? So this becomes even a bigger problem the more we go towards more complex systems, right? And this is one of the use cases that we also had. We're in an environment that there were a lot of microservices, and we wanted to figure out a way where we can actually identify issues that are hidden in the system, and we would know that they will come up at some point. We don't know when, we don't know how, but we knew that we are not that very confident in managing that. Now, this is where chaos engineering comes into play. And you're going to hear a lot about chaos engineering over the next couple of days. So I'm not going to go too much into what is chaos engineering. I'm just going to give a simple definition. Well, the official definition is the one that you read now on the slide, that is the discipline of experimenting in production in order to build confidence in the system's capability to withstand turbulent and unexpected conditions. That's that's a very long sentence, a very complicated one. Simply put, chaos engineering is resilience testing in production, and the goal is to uncover hidden issues, right? Issues that will come up during the worst times. Now, this sounded very interesting for us, right? Because this is something where we actually needed to do rigorous testing and try to identify these bottlenecks and these hidden issues. A few words about some important principles for chaos engineering, which I really think are important. I will not dive a lot into those things, but it's good to have an overview, right? So that you can also see why it's different from other types of testing. Now, in chaos engineering, there are 5 important principles. You start with your steady state, and a steady state is essentially how your system, I don't want to say application, it could be more than one applications, how your system behaves under normal circumstances. And by normal, I mean other regular traffic, for example, not when there is extraordinary traffic or during high peak periods, things like that, right? So this is how your system behaves normally. Then you make a hypothesis, and you hypothesize that if I do this, or if, I don't know, CPU increases to 100% CPU utilization, then this will happen. My application will crash, right? So you make a hypothesis and you try to predict what will happen. Then you design an experiment for it to implement or validate or disprove the hypothesis. You execute that, you get your results, and this is the important part here. You don't stop there. You find what's wrong, and hopefully you do the fix and you try again. You have a constant feedback loop that you create a hypothesis, you try to disprove it, you fix, and you retest. This whole loop is one of the key powers of chaos engineering. Now, this sounded very interesting for us, right? Then the next question is, how do we do that? All right. Yes, we want to use chaos. How do we use it? Well, we're working with cloud native technologies nowadays, right? So for us, Kubernetes it's typically in the picture. So we wanted something that is Kubernetes native and open source, right? There are also commercial products out there, but we really wanted to focus on open source. And there are 4 other elements that were key. First one is observability, right? That the whole framework needs to be observable. And this is quite important because if actually now you're doing some testing and you don't have very good visibility on how the testing is progressing, if things start to fall apart, there's always going to be the question, is it the experiment that's at fault? Is the application failing because it's supposed to be failing? And suddenly all these questions arise and you don't have very good visibility of what actually is happening. So that is key, that we know that the experiments are being it'll be monitored, and there's good logging and tracing and all of that. Secondarily, manageable, right? Manageability. Imagine if I have 500 microservices and I want to execute simultaneously experiments on all of them. It will be a lot of manual work if we don't have something that is automated, declarative, and easier to manage, right? Then it will, most of the time, will be dedicated on managing the experiment instead of focusing on the application that is actually under stress. Then, security. We mentioned the word production, right? So this is where business happens, and it's important to treat production in a very secure manner. So it is very important that we treat security very carefully here, and we don't allow a lot of windows for things to go wrong. Things like controllable blast radius, as we say, or controllable chaos that you can revert if things go wrong, for example. All these things are important here. And finally, extensible. Even if you Google now, you'll see a lot of experiments, right? A lot of CPU experiments, memory experiments, network experiments. But I can guarantee you that there are always going to be tailor-made cases for you. That you're going to need a custom requirement or a custom experiment that you're going to fit your own case, right? So it's important to have something that is easily extendable. Right. So we got our framework. Let's say, okay, let's build something that complies with these requirements. Next question we wanted to answer before we actually dive into the solution is what kind of experiment, right? Like I said, there are hundreds or dozens of experiments that you can do. In our case, or in general microservices, networking is something that gets impacted a lot when things become very complex, right? Slow responses, latency, the critical path of applications of requests become longer and longer. So we wanted to start with network. And we said, let's find an experiment, or let's develop an experiment that allows us to be really in control of our blast radius or of our targets. If we are able, for example, like it's in the picture, to introduce latency between one application and one of its dependencies, another application, despite if actually application A in this case connects to 20 more endpoints, only on one-on-one ratio. If we're able to do that in a good way, then we can start slowly to expand our system. Then we can target two dependencies, the whole interface, more applications of their interfaces, and then you have a very good way or a very granular way of creating chaos in the network, even up to a one-on-one ratio. That sounded very interesting, a very interesting idea. So we started looking into, all right, how do we solve this, right? And I'm going to try to guide you through also our thought process and our experience through that, and also what's actually the solution. This is the picture, right? We have production Kubernetes environment. Applications are running there. Dependencies internal or external to the cluster. Pretty standard stuff. What we wanted to see is what can fit into that blue box that is empty in the picture from open source, from the open source world, right? We looked at several tools and frameworks. I'll not go into how we chose each one of them. We also wrote a blog. Feel free to read it. But essentially, we decided to go with Litmus. Now, a few words about Litmus. I know that you'll see a lot more about Litmus than in our talks as well these days. I will just mention that the parts that are important for our discussion today. So Litmus is essentially a chaos engineering framework, right? And it is actually an operator. It's an operator that gets deployed in a cluster in its own namespace and is able to orchestrate and manage experiments from there in the cluster, right? Now, there are certain custom resource definitions, CRDs, that you can use to define and initiate your experiment. What happens when you start an experiment, and this is the interesting part, there is a chaos runner, you see the blue box there, that gets deployed in the application namespace. It could also happen from the Litmus operator namespace, but there are different modes in Litmus. Let's assume now that this is the mode we are choosing. And that runner is essentially setting up the experiment. After that, and this is the interesting part, for us, the green boxes are the actual pod that executes the experiment, right? If you want to, let's say, to increase the CPU of the pod as a test, this is going to be the one that's going to execute the actual experiment. Now, the differentiator for Litmus that made this interesting for us is that you could use your own runner. You could use a native one, a Litmus native one, but also you could use other tools like the ones we were investigating in the previous slide, like Pumbaa or Chaos Toolkit, and use them to execute the experiment, and Litmus to orchestrate the whole process. This provided a very good extensibility for us, because then we could really go and define our experiments as we wanted them to do. Now, as a first step, we tried Litmus operator, right? So we deployed Litmus operator, and then we tried Pumbaa as our executor, right? As the one to execute the network experiment that we want. Well, that worked partially. And Pumbaa is, a few words about Pumbaa, is another tool. It's not a framework. It's not about orchestrating or having good observability or managing experiments. It's more about executing them, right? It can create network latency, for example. It can increase the CPU utilization of the pod. It can delete pods. It actually does these kind of operations, but it's not about management, right? It's an executor. How Pumbaa is developed, though, it didn't allow us to target a specific IP, for example, or a specific host name. It allowed us only to target an interface, Ethernet 0, for example. This worked for the red use case that you see here, right? When we wanted, for example, to target an application and then all of its connections. Then it works. But it doesn't work for the green use case, which is the one that we were mostly interested in. That triggered us a bit more, and this is where it starts to become interesting and a bit more complicated. That Pumbaa, under the hood, is using what we call traffic control. Traffic control is a Linux utility that basically enables you to manipulate traffic in Linux, right? As you see also in the right picture, right? When we're talking about networking layer in Linux, you have the network interface controller, your NIC as it's called there, and also you have your packets. In between, you have queues or schedulers. These schedulers are responsible for routing the right packets to the right interface and in the right way. This actually triggered us to think that, okay, maybe we can leverage traffic control to really make tailor-made custom queues that we can send our packets to a specific target. Just for reference, so you can see how low level that is. I've put in here the OCI model, right? And probably you've seen that, all the different layers for networking. And traffic control sits between the data link layer and the network layer, which is already low level. It's already lower than TCP UDP communication, or of course the HTTP or application layer communication, right? It's actually sits between the layer that forms packets in Linux and the layer that sends them to an interface. So very powerful, also very low level, right? So we need to be very careful of what we are doing there. But that's a really interesting, right? So our next question would be, how do we make use of that? How do we use this? Now, this is actually the end goal that we wanted to achieve using traffic control under the hood. I'm going to briefly explain this, right? Again, we have the packets and the interface. Now, in between, our target is to create a flow for these packets that will be directed to a specific IP, and they will have latency. That's essentially what we want to do. Of course, not only one specific IP. If we can do it for one, we can do it for 2 and 3 or whole interface, but at least we should go up to just one IP also. First thing we do is we create a new queue or queue discipline. By creating a new queue, you basically create a new scheduler where the packets will be directly to and to a specific interface. After that, you create your filters, right? And filters are used for the IPs and ports, right? So you can create a filter that says, all right, direct these packets to this IP and this port, and this IP and this port. And you can have as many filters as you want. With these two steps, we have basically created our queue, shaped it, but nothing is happening yet. We haven't added any delay, we haven't touched the packets yet, we're just creating another route for them. Now, this is where the third step, which is the class that I'm saying here, is making the actual delay happen. For that, and a class is basically an attribute that you add to a queue discipline, right? It basically characterizes the queue discipline that you have created. And we use for that an enhancement of traffic control, which is called network emulation. And as the definition says, it emulates network conditions. And you can delay packets, you can do packet loss, you can packet duplication, you can manipulate the packets as you want. Now, with these two steps, we have created this workflow that essentially, just to repeat now how the whole picture looks like, we have a new queue that filters for specific IPs, and we're adding also latency to that. So basically, we're actually achieving what we wanted to achieve. So that works. We have, in this way, we can use traffic control for just one IP out of all the connections that are in that interface, or all the connections. It's basically up to us or up to the user how they want to define their experiment. For that, we didn't use Pumbaa anymore. We used the LitmusGo native runner, which we actually built this capability from scratch. And now it's also part of the open source runner that you can find in the community. And this is the demo we're going to show in a few minutes is going to demonstrate exactly that. Before we go to the demo, a tiny bit, which I actually personally find is the coolest part of the whole solution, but it's a bit more complicated, right? I don't know if you already are trying to think, cool, traffic control, nice, right? But how are you actually going to implement this? How is this going to be possible? And this was, I think, the interesting part, right? Now, one solution, which is not the one that we went for, but one solution would be, all right, what do we need? We need traffic control to be installed in the target, right? So we can use traffic control in the network namespace, in the network interface of the target. For example, in this picture, application E. And for that, we could target application B or B or everything, right? But that didn't work out. Because as you can already see, that would require elevated privileges for every application that needs to use DC, traffic control, or all the, let's say, or basically having in all applications DC installed. That didn't go very well with us, right? Or at least that was, imagine having a production cluster and all your applications have very elevated privileges to manipulate the network. Not ideal. So what we ended up doing is using what our Linux facilities, basically a network namespace of Linux. As I don't know if you heard about this, but just to briefly explain what that is, you heard about Kubernetes namespaces, right? Which is a grouping of resources in Kubernetes. Similar mindset is also used in Linux to group together resources that they belong together, and they call them namespaces. For example, we have PID namespaces for processes. We have C group namespaces for C group resources. We have user namespaces for users in Linux. Similarly, we have the network namespace, which is essentially a virtualization of the network stack of your target, right? This allowed us to use the network interface of application E, but just using its network namespace from somewhere else, not by having to, I don't know, exec or logging into that pod. That was interesting. This is more towards what we want to do, because then we don't have to install traffic control anywhere. We just need to install it on the LitmusGo runner. And from that point, we could use an applications network namespace. To do that, and this is where it became more interesting, we need the process ID of that process that we want to use the network namespace from, right? In this case, the container PID of application E. Without this, Linux doesn't know which network namespace you want to use. So to find the container PID, you need to be on the same node as the application, right? Because that's from the node level, and the best way to get that is from the node itself, right? So what we actually ended up doing, and with the community we enhanced Litmus as well, is that you can use node selectors in your manifests, and as long as you know in which node your target is running, then you can deploy the Litmus runner only on that node and not on any other node that is not relevant for the experiment itself. That way you control a bit better the windows that you leave open for things to go wrong, because you only target the node that you want to target, and you can use taints, tolerations, things like that to clean the node before you actually do the experiment. So you can do all these kind of things. And essentially what you achieve is this workflow to be working. And now, right, this can also get complicated, so feel free to ask a lot of questions, but now it's time for our demo. And maybe before we dive into that, if there are any questions, we can take a couple of those, and then we'll go and break some things.
It looks like we have a question. Is this only applicable at application level? Can we use TC in multi-layer such request handler to microservices, etc.?
You can use TC pretty much anywhere, because when you see where actually what traffic control influences is layers that are even below application layer, right? So we are influencing packets. So whatever is using network, you can use traffic control to influence it. If it's application or database or anywhere or anything, you can use traffic control to manipulate the queues there. Of course, with the proper care, but essentially the power of traffic control is that you directly manipulate the queues on the packet level, or the lower levels, right? So we're not even talking about protocols at that point yet, right?
Another question, can you share some of the challenges faced with respect to injecting chaos on production?
Yes, good question. Let's pick that up after the demo. I think that's gonna maybe trigger even more questions, but let's keep that for after the demo. Okay, good question. Perfect. All right, now time for the fun stuff. What are we gonna do? I've set up Microservices Hipster Shop demo, which is a Google Microservices open source demo that you can also use for your own demos, right? It basically simulates an e-commerce website. It uses HTTP for external communication, it uses gRPC for internal communication, is some cache there. So basically it has pretty much services that you will encounter in most websites like this. Of course, most of the functionality is just for the demo, right? There is no real business logic behind it. But what I'm going to do is I'm going to try to create 2 seconds latency for 1 minute between the front end and the checkout service. I'll show you how the site looks like. But essentially, the checkout service is the one where you go in a website, you put things in your cart, and you click purchase, right? So this is where the money comes in, an important component, right? And what I hope to see is that only between those 2 microservices there's going to be latency, and the rest of the applications are going to work fine. And also, once the experiment is done after 1 minute, even this connection between front end and checkout is going to be stabilized. So we're going to revert back to wherever we were before the chaos. That's the hope. Let's see if that's going to happen. Right, so this is how the hipster shop looks like. You can go click, browse products. There are some demo products here. You can add them to your cart. I just have also the network console open for reference. You can see requests that they're taking a few milliseconds, right? You can empty your cart. And the part that we're going to add latency is that, let's say we want to buy this, yeah, pretty cool actually, vintage record player. We're adding to cart. And this button, once you click that, is essentially purchasing, right? So this is the button that we're going to add latency to. Now I took like 400 milliseconds. Yeah, that's typical. It's just on my network. If I try to do that again, it will take just a few milliseconds, right? Now it's 100 milliseconds. It seems to be working. Now, I'll briefly show you how I'm going to do this. Right, I've deployed Litmus in a GKE cluster. I've deployed the hipster shop also there. I've prepared everything. Also, by the way, the code is on a repo that at the end of the presentation you can also get the link and try it out for yourself. The important part that I want to stress here is how actually it's configured. We have a label here, which is the app frontend, and essentially this dictates what's our Chaos target. What's the application that we're going to create Chaos from? And here we have a destination host. We can have more than one. I'm just having here only the checkout service, right? If I comment that out, then it will target the whole interface, for example. And here we have 2000 milliseconds, so 2 seconds and 60 seconds worth of Chaos. Right, so now I'm going to go to my shiny terminal. We can see, let's clear some stuff. We can see that the hipster shop is running, right? Everything is running. We also saw it live. Nothing else is happening. What I'm going to do is just apply the Chaos engine, right? Just going to apply that. Now, if I start to get the pods and see what's actually happening, right? We see that there is already a pod that the Chaos runner that started, that prepares the experiment. We have a first helper pod that has started, and now this is our Chaos runner, right? So if I do shop logs run, we're going to explain this afterwards, but we see that this is already has started. Okay, now if I go and start clicking on things, this is still fine. A product adding to cart is still fast. Now is that. Okay. Now it took 2.11 seconds, right? So it's the 2 seconds we added plus some more, of course. Let's check that everything else is okay. The currency application is fine. Checking the whole cart is fine. Okay, if I buy something again, place order, again, 2 seconds. Good, okay, our experiment is working. Everything else seems okay. I can click on things fine. So for now, I'm not noticing anything out of the ordinary. Of course, there's some slight delay, but nothing out of the ordinary. 60 seconds are passed. Everything is done. Now, if I go back, I hope that the checkout service is actually working fast now. Yes, so it's back to the millisecond level. Cool. I'm happy on one hand that nothing was happening, but on the other hand, actually, I want to break some things. So, well, you know what? I'm just going to comment that out. Oh, I'm just going to comment that out completely, right? And if I do that, then what we will expect is that the whole interface of the front-end application will be, we will add 2 seconds delay to all the connections of the front end. Hopefully that will be more stressful. Now, what would I expect, right? If the applications are resilient enough, I'll still see latency everywhere I click. But like a cart or a product, everything should have some latency, at least 2 seconds. Let's try that again. Apply the Chaos Engine and getting the pods. Let's see, because now it's time to test the real resilience of Google's microservices demo. Maybe there's something we can fix there. So this has started. We don't have to check the logs, right? It has started. So let's check our website. I click here. Oh, that's more than 2 seconds. Something is going on. I click card and there's definitely more than 2 seconds delay taking me to card. Oh, now I can be reached. Let's see what is happening. Oh, the front end is actually not running anymore. So apparently, what happened is that this 2 seconds delay to the whole interface crashed the front end process inside the container. Something that we didn't really expect, right? You can still it's not running. So I should not be able to do anything here. No. So that's something to investigate for later, right? Why did it crash after adding 2 seconds of delay? Now our test is done and the front end is back up. So if I refresh here, all right, we're back in the game. But that was a bit concerning. If I was in a SRE and my whole platform went down because, well, not platform, but the whole front end service went down because I added 2 seconds of delay, then I would have to check this. Right. So we broke some things, and that's good. But like I said, we should not finish there, right? The next step will be to identify what the cause and fix the problem. Hope you enjoyed the demo. Some quick takeaways, and we can take some questions. Right. Again, traffic control is super powerful. You can do a lot of things with it, but definitely be very careful how you use it, what privileges you use. Always use things like least amount of privilege, and always be super careful with security. Closing the loop, I mean, now we found an error, for example, or at least there's something going on with the front-end service. Ideally, we should go back, investigate, retest until we are happy with the outcome. And one lesson that we learned is there's always going to be a tool that is fitted for your needs. There's a lot of open source tools. The community is super vibrant and super eager to help. Take a proper look on what are your needs and choose the right tools for you. Where to go next? Contribute to the community. Like I said, we're really pushing to make Chaos Engineering or cloud native Chaos Engineering more and more applicable to use cases out there. Create more experiments. There's never going to be enough of them. Automate and orchestrate using more workflows, right? I think this is the next level. This is the next front that we're going to have to tackle. How do we automate and orchestrate many experiments? And if you haven't started already, start testing production with care, of course. Links and references. There's demo code on my repo. It's open source. You can use it. It just spins up the demo that I showed you today. You can start looking at the Litmus docs and how you can create experiments there. And there's also the Hipster Shop repo that if you want to break it as well in your spare time. Yeah, that's all for me. Happy to take any questions, and I hope that you all found it useful. And from tomorrow, you're gonna do more chaos in your own things. Thank you. Do you have any questions? Can't hear you, Mohan, I think.
Oops, sorry, I was on mute.
That's the quote of 2020, right? You're on mute, everybody.
Yeah, so let's start with Omkale's question again. Can you share some challenges with respect to injecting chaos on prod?
Good, indeed. Challenges, I would say the more of the challenges are on the cultural level. I think chaos engineering is a mindset shift from where the testing is supposed to be done anywhere else but production in actually happening in production, right? Which was typically treated at the no-touch environment. So for me, I think the main challenge is to create a confidence and the sense of being in control when you're executing chaos in production environments. This is a gradual thing, right? Of course, that's why I was stressing a lot security and blast radius and things like that. That just because we want to break things, we don't want to do this without control, right? So I think the technical challenges were something that you can bypass. There are ways, there are tools that you can do things. The main challenges is around creating a cadence of using chaos tests consistently in production, and more importantly, following up with the identified actions that the teams need to do and retest again, right? And do this and make this part of the even CI/CD pipelines or part of the normal workflow of people. So yeah, I think challenges were more around making people confident that this is a good idea, basically.
So one more question related to that. Do you always experiment only in production? I don't think he's talking about in general when you are doing chaos engineering. Do you want to experiment only in production or also set up a production like environment with the same results?
I think chaos testing should be done anywhere, everywhere actually, right? Not only production. It should happen from all environments and ending up in production. But that should be the goal, right? It's always going to be that the main test should be in production. The reason is that you want real traffic. You want real users, maybe not all users, just a part of them, but you want real traffic to test your hypothesis. But it's certainly something that is not only applicable to production. You should do it also as part of your regular dev flow, maybe in a smaller scale. You're not testing a whole system, maybe just testing your application and its dependencies, and then growing that as you go more to other environments, like integration environments and things like that. But it's absolutely for every environment, and I would say even for every department, or let's say it's for developers, for testers, for sysadmins, for security teams. Everybody can chaos test their tools. You can chaos test your GitLab self-hosted setup. You can chaos test your Kubernetes cluster itself. You can chaos test your nodes. You can go pretty much crazy with the amount of different layers that you can test. So really good question, and yes, I think it's for all the environments and ending up to production at the end.
So another question from Ritik.
Yeah.
Any specific capabilities you would expect or build in the tooling to ensure that things don't go out of hand? What are the most important observability aids that ensure this?
Right. Going out of hand, right? So one of the things that, and it's about building the psychological safety that you are in control of things, is about instantly being able to stop an experiment. For example, in Litmus, there is the ability to immediately stop the experiment by patching the CRD the chaos engine that you have deployed. And actually, in less than milliseconds, it's actually stopping everything. That is the easy part. Stopping an experiment is the easy part. Where is the difficult part is when things get out of hand. How do you stop the widespread chaos? So this is a different problem and actually a bigger problem, right? So what should be the aim is how do you avoid spreading the chaos? You can do things like labels and annotations on the things that you want to target, right? Litmus has a nice 3-layer check that checks the deployments, its annotations, its labels, then checks the labels of the pod as well. So there are a lot of gates that need to be correct so that you create chaos somewhere, right? So it's also the part of the orchestration of the experiments, how well you're controlling that. And then it's your executor, in our case, traffic control, that you allow it only the privileges that it needs. For example, you don't give it sysadmin access to your resources because it doesn't need that. It needs netadmin access. If you're using OpenShift and things like that, when you can have security constraints SCCs, definitely make use of them and make it only using the resources that you need. These are the types of measures you can put in place alongside with big panic buttons that you can just push either through a pipeline or through command line directly, and you can stop immediately the experiments. The observability side is also super important. That's why it's one of the key pillars. What I always try to say is that observability should be that good that you don't have to look at the experiment anymore. You just look at your application and how it behaves. It means that you have readily available your logs. It's easy to trace what's happening in the experiment. It's easier to monitor, to have metrics. How is the CPU utilization, for example? How is the network latency going? And having this more holistic view of what's happening, very available. There are ways you can do that, but definitely the focus should be to have observability really mature in order that you don't have to pay attention to the experiment, and you pay attention to your application and see what's happening there. So that's the purpose, right?
So a question from Ben: how did you make people comfortable that the experiments can be run in production? Is it simply showing them the control and limiting the blast radius, or were there other useful arguments?
So of course you start with why you want to do this, right? And when you explain that, or when also the people that they let's say administer or maintain production clusters, they have felt the pain of what it means to something to go wrong, and you explain what actually chaos will do for them, they are already start to see it positively. Where you need to put effort is to put all the security and control measures that are needed in order to avoid that. For example, Pumbaa gets deployed as a demo set. Of course, you can use node selectors and tolerations to make it more fine-grained, but by default is a demo set. If you forget to put a node selector, for example, and you deploy it in production, it's going to deploy a very privileged Pumbaa pod in all of your nodes, which is even not needed anymore. This kind of approaches, this approach made very nervous the people behind the clusters, because they said and justifiably, that's a security breach, that's a security vulnerability. That's why we went with approach only we deploy where we need to, and maybe we put some taints there from other applications to get out of the node before we test. Then you can isolate on one node your test, right? When you put measures like that, make people feel more in control. So it's a mixture of technical capabilities of the tools you choose, that need to be the right ones, and also passing the right reasoning behind. So what will be the benefit of this? At the beginning, it can be difficult, but I can tell you after, at least for us, it was a matter of a couple of weeks to already identify a major issue. And then you already start getting more confidence by the people behind that.
So another question. So I'm just paraphrasing this. Are there cases where you have seen where you absolutely cannot test in production?
Absolutely, you can. Sorry.
Absolutely cannot test in production.
Test in production. Yeah, I think I wouldn't say so. There's always going to be something that you can test. For example, even on the infrastructure level, you can test even your monitoring tools. Are they resilient enough? For example, all this monitoring redundancy that people are talking about, for example, what happens when your observability goes down? Who monitors the one that monitors things, right? This is things that you can chaos test without impacting your production applications. You can test your CI/CD tools. You can test your nodes. If there is a case, or if you're in a situation that there is it's really difficult to make this change more of a mindset point of view, I would start from less impactful things, but still showing the value in more auxiliary or supporting systems like those. And then you slowly get your buy-in to start testing maybe in the less impactful applications that they don't have maybe direct interaction with the users. It's more of a supportive or auxiliary application. And go from there, right? So the way that you can a company can adopt this varies, right? There is no one recipe, but there's certain things that you can test that they have no direct impact on things, and still you get to build this confidence in and even build the capabilities, right? Maybe you need time to build a chaos engineering framework that fits your needs, and you can't test really in production anytime soon. Pick something that you can test more confidently, even if it's not an application that is customer facing.
All right. I think we are well past time. Thank you,
Great.
Andreas. Thank you, everyone, for joining. We have the next session starting sometime soon. See you all in the next session.
Thanks, everybody. Feel free to reach out for any further questions. Happy to help. And have a great rest of